So, a valid definition of state would be to only look at the last observation, for example, and just ignore everything that's come before, or to look at the last 4 observations. That's actually what we did in Atari. Pretty simple. Okay. But there's many different definitions of state, and what I want to pick apart now is at least 3 different definitions of state to understand what they really mean and how they relate to each other. So the first definition is what we call the environment state. So the environment state is basically the information that's used within the environment to determine what happens next. So if you think about it, there's some in this world, imagine this is the robot interacting with some real environment. That real environment has some sort of set of numbers determining what's going to happen next. Or if this is the Atari emulator, the emulator has some internal state that's going to decide what that emulator does next. Or if this is a factory, what happens to that factory has some process that's going to decide what happens next. And there's some set of numbers that determines what happens next from the environment's point of view, based on what it's seen so far, its history, and there's some state that summarizes everything it's seen, and which will spit out the very next observation and reward. And so we call that the environment state. This is literally, what if you kind of informally were to say what state is the environment in, it's the set of numbers that is contained in here, the information that is necessary to determine what happens next from the environment's perspective. So the special thing about the environment is that it's not usually visible to the agent. So, we don't get to look inside our crystal ball, and we don't get to see everything that's happening within the environment. If you've got some robot walking around in the world, it doesn't know the state of all of the atomic configuration of Ayers Rock in Australia. It only gets to see what's in front of it in this video stream that's coming through to it right now. So the environment state, this set of numbers that's determining what happens next, isn't usually visible to the agent. So it's more like a formalism that helps us understand what an environment is than something practical that helps us build our algorithms here. Our algorithms cannot depend on these numbers. Our algorithms don't see these numbers. Our algorithms just see the observation coming in and the reward and the actions coming out. And furthermore, even if we could see this information, sometimes it might not be the right information that we would like to use to make effective decisions here. So again, the configuration of Ayers Rock isn't probably very relevant to the robot that's wandering around this room right now. It needs to be able to look at its own stream and understand what's locally around it to be able to make good decisions. And so actually having its own subjective representation may be a good thing. Yes, question?
If you put a lot of agents together influencing the same environment, do you get any sort of self-organized behavior patterns or anything like that?
Okay, so the question is about multi-agent systems. So I just want to say one thing about multi-agent systems, which is essentially they're beyond the scope of this course, but let me just briefly say that from the perspective of each individual agent, it can consider all of the other agents that it's interacting with to be part of the environment. So from the perspective of one brain here, the fact that there are other brains wandering around in this environment doesn't really change the formalism. It doesn't have to change the formalism. There's just one agent interacting with them. Your question, I think, is whether the emergent behavior shows some patterns between the brains here and the brains there. It can, and there's a lot of work on that, but it's kind of beyond the scope of what I'm going to talk about in this course.